So we know now that the business of knot theory is the business of finding knot invariants that are capable of telling different knots apart one from another so that we can hopefully classify all knots that are out there in the universe. But as we've already seen, not all knot invariants are created equal. They're not all as powerful one as another. Some of them are easier to compute or find, perhaps, but what we want ultimately is an invariant with enough power to definitely always be able to tell different knots apart. The numerical knot invariants that we've seen, the crossing number, the bridge number, the unknotting number, while they're easy to understand, they're not particularly powerful in terms of telling different knots apart, particularly as the knots get more and more and more complicated. They're also not always easy to find either. So what we want to do is take it a step further and assign to a knot not an invariant which is a number, but an invariant which has more to do with algebra. So our next step is to discover what's called an averaging process. We're going to explore how coloring a knot with different colors on the arcs of its diagrams can help us to illuminate the structure of a knot, and look at how an averaging equation can help us to distinguish a valid coloration from an invalid coloration. The hope being that this equation can give us a foothold into not just using algebra at the level of sort of 8th grade algebra to classify knots, but we'd ultimately like to use even higher algebraic abstract structures to classify knots and hopefully encode as much information as there is to know about a given knot. We get there by starting with the process called coloring a knot. By definition, a k-coloration of a knot diagram is a way of assigning to every arc in that diagram a number, a whole number from 1 up through k. So k-coloration means I have k different numbers. Each number represents a color, if you like, that we're going to work with. But we do so in a very particular way. We do so by insisting that any time that 3 arcs in a knot diagram meet at a crossing, and every crossing in a knot diagram does have 3 arcs, the over arc and 2 under arcs that meet at that point, that at every crossing in the diagram, either all 3 of the colors that I assign to those arcs all have to agree, or all 3 of the colors that I assign to those arcs have to be all distinct. So in the first situation, if I think of maybe the color 1 as being the color red or something like that, then it would be okay if I colored all 3 of the strands incident at this crossing red. It would be okay if they all had the color value of 1. Or it would also be okay if, for example, all of the color values that I assign at this crossing are different one from another. So maybe I have 1, 5, and 9 or something like that. So this situation is okay for a valid coloring. This situation is okay for a valid coloring. And any way in which we would like to mix and match these in a given knot diagram is still okay. We don't need every crossing to be one of these types or the other, but every crossing has to either have all 3 of the same color or all 3 distinct colors in order for us to have a valid coloring. So for instance, here's a 6 crossing knot diagram, and if I think of the numbers in my color box over here as colors, I can color the 6 arcs in this diagram with only 5 different colors. So this is a 5 colorable knot. Notice that the one color that we got to reuse in this diagram was the color green, because we were able to color this arc green and that arc green because somehow they were far enough away in the knot diagram that they didn't have to interfere with one another. The one thing that we cannot do for a valid coloration is to make 2 colors at a crossing the same while the third color is different. So that's the one thing that we are not allowed to do. So supposing that I have a knot diagram that has n arcs in it, then we might ask, for what values of k will this knot be k-colorable? Well, every knot diagram will always be one colorable. We can always just take a single color and color in the entire knot diagram the same color. We call that a trivial coloring. That always works for any knot diagram because it meets this sameness criterion at every single crossing. Also, for a knot with n arcs in its diagram, we can always find an n coloration of that knot diagram, because if I choose a different color for every single arc in that diagram, then I'm going to meet this distinct criterion at every single crossing in that knot diagram. So every knot of n arcs, every knot diagram of n arcs is always one colorable, and it's always n colorable. So the real interesting questions are, what about the in-betweens? For what values of k between 1 and n is it possible to have a k coloration? Well, k equals 2 is out, because if I only have 2 colors to work with, and I try to use 2 different colors in my coloration, then as soon as I use 2 different colors at any crossing in my diagram, the third arc in that crossing also has to be a different color from the first two, and if I'm already out of colors, it's impossible for me to do that in any way that's not trivial. So 2 colorability is not interesting at all. Every 2 coloration is really just a 1 coloration. We only ever get to use 1 color. So the first interesting value of k for which we can ask questions about colorability that aren't trivial is k equals 3. So we might start by asking ourselves, is whether or not a knot is 3 colorable? First of all, is that a knot invariant at all? And second of all, if it is a knot invariant, just how powerful of an invariant is it to distinguish between different knots? First of all, is colorability actually a property of knots, or is it a property of diagrams? Because anything that we define based on diagrams, arcs, and crossings is, unless we check to make sure that it doesn't depend on how we draw the diagram, or it doesn't depend on any of the Reidemeister moves that we could apply that give me the same knot with a different diagram, until we can verify that that property is invariant under the 3 Reidemeister moves, we don't know that it's not a property that might depend on the diagram for knots. Fortunately for us, every question about colorability and valid coloration is a question that does not depend on the knot diagram. So for any given knot k, if I have 2 different diagrams of k, then one of those diagrams has a k coloration, a valid k coloration, if and only if the other one does. And to prove that, we just have to verify that valid colorability is invariant under the 3 Reidemeister moves. So for type 1, which is the twist maneuver, suppose that I have a strand in my knot diagram, an arc that I've colored 1 color. And then I apply a type 1 Reidemeister move, twist, to it. Can we still come up with a valid coloration for my new diagram, given that at these open ends that connect to the rest of the knot diagram, we were coloring this arc red? So given that these have to be red, can we still come up with a valid coloration for this part of the knot diagram? And the answer is sure, because if this arc here is red, and this arc here is red, well, this arc continues around to be the same as this arc. So if they're all red, which they're forced to be, is that a valid coloration? Yes, it is, because valid colorations admit the possibility that all 3 arcs at a given crossing have the same color. So this is fine. Type 1 Reidemeister move preserves k-colorability. How about type 2? If I have 2 strands of different colors, so if they had the same color, we could do the same kind of trivial thing over here. So let's assume that they have different colors. If I have 2 strands of different colors that do not cross, and I apply a type 2 Reidemeister move that slides one of them over or under the other, can I still have a valid coloration for this new thing? As long as I have a 3rd crayon in my color box, the answer is yes, because I can just color that new arc that we created in this Reidemeister move. I can color it with the 3rd color and have a valid coloration, because at each 2 of these crossings, all 3 of my colors are distinct. So the question of colorability is preserved under the type 2 Reidemeister move as well. How about type 3, the so-called slide? So if I start with a crossing right here that has 3 distinct colors in it, again, if they were all the same color, we could have a trivial answer to this. So I'm going to assume that these 3 are all different. How am I forced to color this strand over here, assuming that I have at least 3 colors in my crayon box? Well, I have to color the strand that's in between the blue and the red arc here. I have to color that one green. And similarly, I'm forced to color the one that's up here red and the one down here blue. So I can color this diagram. Can I still color that diagram after we slide that vertical strand from the left side of the crossing over to the right side of the crossing? The answer is yes. I just have to repeat that same process. In between the red and the green arcs, I am forced to color blue, and then likewise on the top I'm forced into green, and on the bottom I'm forced into red. So each one of the 3 Reidemeister moves preserves the notion of whether or not a diagram is k-colorable. And therefore, k-colorability is not a property that defines diagrams of knots, but is a property that belongs to the underlying knot itself. And that makes it valuable as a tool for distinguishing between different knots. What we hope is that colorability is a powerful enough tool that we can completely tell different knots apart. In other words, when I have 2 knots that have the same colorability properties, I would like to know for sure that those 2 knots are exactly the same knot. If we can come up with a way to prove that that's true, then we've discovered the Rosetta Stone, a complete invariant that can tell any different kinds of knots in the universe apart from one another. So let's look at the k equals 3 case. Again, the smallest value of k, for which k-colorability is an interesting question. How can we turn the question of colors on arcs in a knot diagram into a question about algebra? How do we discover what I call the magic equation that can tell us for sure whether or not we have a valid coloration for a knot diagram. Let's think about the two cases in which a knot coloration is valid at a given crossing. In the first case, where all three of my colors are the same, if I think of my three colors as being 0, 1, or 2, because I only have 3 crayons in my crayon box, if I think of X, Y, and Z as belonging to the set 0, 1, and 2, if all three of them are the same, and I choose to add X, Y, and Z together, then that sum is either going to be 0 if all three of them were 0, it's going to be 3 if all three of them were 1, and it's going to be 6 if all three of them were 2. So in the case where all three colors are the same, the sum of the three colors is going to be either 0, 3, or 6. In the case where the three colors are distinct, one of them is going to be 0, the other is going to be 1, and the third one is going to be 2. And so regardless of what permutation they happen to be in, if I add them together, I'm going to get a sum of 0 plus 1 plus 2, which is 3. So what we notice is that for these two valid coloration cases, the sums of X, Y, and Z have to be either 0, 3, or 6. We can also check that at any invalid crossing, in other words, a crossing at which two of the colors are the same but the third one is different, we can check all of those cases and see that the sum of X, Y, and Z in those cases is 1, 2, 4, or 5. So it seems like there's a lot of different results here, but they can all be unified by the observation that those valid colorations give me a sum at the crossings which is a multiple of 3, and those invalid colorations give me a sum at a crossing which is not a multiple of 3. Therefore, we get what's called the magic equation. I call it the magic equation. It says that 3 integers x, y, and z are either all equal or all distinct if and only if their sum is a multiple of 3, or x plus y plus z is congruent to 0 mod 3. What that does is it gives us a way to turn questions about 3 colorability of a knot into a linear algebra problem over the integers mod 3. So as an example, if I take this knot diagram, it has 6 arcs in it. I happen to have drawn an alternating diagram for this knot, so it has 6 arcs and it has 6 crossings. Let's label the 6 arcs x1, x2, x3, x4, x5, and x6. I'm also going to use those variables abusively to represent the colors that we assign to those knots. And there are 6 crossings, and at each one of those crossings, we want this equation to hold in order for our coloration to be valid. And so what we get is a 6 by 6 system of linear equations over z mod 3, where each of those equations corresponds to one of the crossings, and we require that at the crossing this equation hold, and each one of the variables is the color that we assign to one of the 6 arcs in this diagram. So for example, at the crossing I've labeled A in this diagram, we have 3 arcs that are incident to that crossing, the x1 arc, the x4 arc, and the x5 arc. And if we have a valid coloration, then the magic equation needs to be satisfied at that crossing, i.e., the color we assign to x1 plus the color we assign to x4 plus the color we assign to x5 has to be congruent to 0 mod 3. I'll do the same process for the other 5 crossings in my knot diagram, and I get this handy 6 by 6 system of linear equations that I'd like to solve over z mod 3. Notice each one of the rows has 3 1 coefficients and 3 0 coefficients. Each one of the columns also has 3 1 coefficients and 3 0 coefficients. So it's not too terrible of a linear system to row reduce as long as we can keep our head straight and do our arithmetic inside of z mod 3. I usually let technology do this step for me, but it's good to do the linear algebra for yourself by hand once or twice to get the feel for it. I prefer Sage, but you can use Mathematica or Maple or any sort of tool that's capable of doing linear algebra over an integer ring, a modular ring of integers. If I find the reduced row echelon form of this matrix equation, and then I rearrange it to discover the free parameters in this system turn out to be, there's 2 of them, and we'll make them x5 and x6 just conventionally. And therefore, the other 4 colors, x1 through x4, we can solve in terms of those free parameters. So when you do out the linear algebra, this is what it looks like. We find out that x2 has to be equal to x5, x4 has to be equal to x6, and x1 and x3 are each equal to minus t minus s. That's the quantity I'm going to call u for the moment. So I have 2 free parameters, which means that I get to choose values for t and s, and in my diagram, t and s represent the colors of the 5th arc, this one, and the 6th arc, that one. So I get to choose how to color those 2 arcs, and those choices are going to determine completely for me how to color the remaining 4 arcs in this diagram. On one hand, suppose I choose those 2 arcs to have the same color, so suppose t is the same as s. Then what's my 3rd color going to be? U, minus t minus s. Well, if t and s are equal, that's the same as minus 2t. And because our arithmetic happens over the integers mod 3, negative 2 is the same as positive 1. And therefore, in this circumstance, u is the same thing as 1 times t, and that's the same thing as 1 times s if I've chosen my two free parameters to be equal. And therefore, what I've proven now is for this knot, if I color arc 5 and 6 the same color, that forces every single arc in this diagram to be colored with the same color. And so what I get in that case is a trivial coloration, a single color coloring all the arcs in my diagram, which is valid, but it's not very interesting. So do there exist non-trivial 3 colorings for this diagram? To find one, we apparently have to insist that t is different from s. And if t is different from s, then we can show that in Z mod 3, u, minus t minus s, is distinct from both t and s. And in that case, we are using all 3 colors in our crayon box, and we have a valid tricoloration. For example, if I choose t to be 0 and s to be 1, then running through these equations, I find out that x2, since it has to agree with x5, has to be 0. x4, because it has to agree with s6, has to be 1. And x1 and x3, minus t minus s, are equal to one another, and each are equal to 2. So if I assign the color red to 0, green to 1, and blue to 2, that gives me a recipe for one way in which this knot diagram can be 3-colored. If I fill in those colors, I find out, there we go. We have a valid 3-coloration for this diagram. And you might notice that because I have a whole lot of other choices I could make for t and s, we can get other 3 colorings as well. Although I think particularly for this knot, the number that we get is up to a permutation of the 3 colors in my crayon box. There's really only one essentially distinct way to non-trivially tricolor this knot, and we're looking at it right here. But this knot is 3-colorable, and that's how linear algebra shows us how. Why does the magic equation work? The real reason the magic equation works, and the title of this component of the presentation, is it works because it's an average. Now, why is x plus y plus z equals 0 mod 3 an average? Well, let's rearrange it to get the z by itself. So z is minus x minus y mod 3. But negative 1 in z mod 3 is congruent to 2, so that's the same as z equals 2x plus 2y. But also, z mod 3 being a field, 2 has a multiplicative inverse. Namely, the multiplicative inverse of 2 is 2 itself. In other words, 2 is the same thing as 1/2 in z mod 3. And so another way to see it is this is the same thing as z equals a half x plus a half y. Just an average. Z is the average of x and y. And that's why it's somehow natural, it's intuitive, that anytime we have 3 numbers where one of them is the average of the other 2, then either all 3 of them are the same, or the average is strictly in between the other 2. So that's what gives the magic equation its bite. That's what gives it its power. And we can generalize that by sort of relaxing the idea that the average has to be halfway, exactly halfway in between x and y, and just relax that and say, well, it has to be somewhere along the line between x and y. So we can think of it as a convex combination. Z equals tx plus 1 minus ty, where t is something strictly between 0 and 1. The motivation for this comes from working in vector spaces. In a vector space, if I have 2 points that are not the same point, x different from y, then I can parameterize the line segment joining x to y using the very same type of equation. I teach this to my multivariable calculus students all the time. R of t equals tx plus 1 minus ty parameterizes a straight line segment in between the points x and y in the vector space, where t equals 0 is going to correspond to the point at y, t equals 1 is going to correspond to the point at x, but if I choose a t in between 0 and 1, I'm going to get a point somewhere in the interior of that line, not x and not y. But if I did happen to have x be the same as y, then we can see pretty quickly that x, y, and z are all the same. So how do we extract that out, that notion of convex combination? Well, the first step might be to think what we really need to do in order to justify that this property, z is either equal or strictly between x and y, in order to make sure that that still works, what we really need in this equation is we need to be able to solve it for any one of its variables, x, y, or z. And to do that, we're going to need for t and for 1 minus t to be invertible. When t was strictly between 0 and 1 a second ago, that was a given. But to extract that out, we'll think of t and 1 minus t as being invertible. We'll relax that one more step and say, it'll be enough, it turns out, that t be invertible. Because as soon as t is invertible, so is 1 minus t. And what that does for us is that also gives us a new magic equation that I call now a magic average. The magic average has the power to now discover not just 3 colorations, as we did a moment ago, but k-colorations for any value of k greater than or equal to 3. Z is equal to tx plus 1 minus ty with the arithmetic done over z mod k. That this is going to give me the same magic property, that either x, y, and z are all the same, or x, y, and z are all different. And it's going to do that as long as t is invertible in z mod k. And t is invertible in the integers mod k if and only if k and t are co-prime one to another. So if I want to detect whether or not a knot is k-colorable, what I should do is set up this magic average for some choice of invertible value of t. So as long as t and k are co-prime, I can set this magic average up at every crossing of my knot, and then do the same kind of linear algebra that we did for 3 colorability a minute ago. So for example, this 6 crossing knot we showed a few slides ago has a 5 coloration just by coloring it in. So if I do this process for this 6 crossing knot over z mod 5, let's verify that the magic average actually justifies this 5 coloration. So in z mod 5, which is the residues 0, 1, 2, 3, and 4, I need to choose a value for t, so let me choose anything which is a co-prime to 5. Let me just choose 4. The reason I like 4 is if we set up this magic average, it turns out to have this really nice form, where the x and the z have positive 1s, and the y has a negative 2 for a coefficient. So I'm going to set that up as my magic equation. If I then take each of the 6 crossings in my knot diagram and I build this magic equation at those crossings, rather than solving this system, I'm just going to verify for you that this 5 coloration that we found a few slides ago is actually valid in the sense that it satisfies this 6 by 6 system. So I'll substitute in for x1 the value 0, for x2 the value 1, for both x3 and x5 the value 2. Those were the 2 arcs that we colored with the same color. For x4 we'll substitute a 3, and for x6 we'll substitute a 4. And when you do out all of that arithmetic, you find out that sure enough, each one of those 6 equations gives us a sum which is congruent to 0 mod 5. And so k-colorability can also be reduced to a linear algebra problem, just done over z mod k, where we've chosen a value for t which is co-prime to k. So this is really cool, and this gives us a lot of computational power to determine, given a knot, whether or not that knot has a non-trivial k-coloration, because linear algebra has so many tools, we can now plug those tools into our study of knots. The next step for us, though, is to take a step further and get even a little bit deeper, and ask, if there's linear algebra here, now, at the table, what's really going on behind the scenes? What are the vector spaces that are in play over which we're doing linear algebra? And are the vector spaces somehow the invariants that we're looking for that are going to classify knots? That's our next step.